redirecting that first block's momentum to point in the opposite direction. In total, there will be 31 collisions before each block is sliding off towards infinity, never to be touched again. What if the first block was 10,000 times the mass of the second one? In that case, there would be quite a few more clacks, all happening very rapidly at one point. Adding up in all to 313 total collisions. Well, actually, hang on. Wait for it. Wait for it. Okay, 314 clacks. If the first block was 1 million times the mass of the other, then again, with all of our crazy idealistic conditions, almost all of the clacks happened in one big burst, this time resulting in a total of 3,141 collisions. Perhaps you see the pattern here, though it's forgivable if you don't, since it defies all expectation. When the mass of that first block is some power of 100 times the mass of the second, the total number of collisions have the same digits as pi. This absolutely blew my mind when it was first shared with me. Credit to the viewer Henry Cavill for introducing me to this fact, which was originally discovered by the mathematician Gregory Galperin in 1995 and published in 2003. Part of what elegant and for being the most comically inefficient. I mean, think about the actual algorithm here. Step 1, implement a physics engine. Step 2, choose the number of digits. Step 3, set the mass of one of the blocks to be 100 to the power d minus 1, then send it traveling on a frictionless surface towards a block of mass 1. And step 4, count all of the collisions. So, for example, to calculate...
Are you sure you can count all of it? Because you can't count all of it with fingers, because you're really gonna break your hand at the age of 573. At the age of 31,415.
Billion times the mass of the other, which, if that small block was 1 kilogram, means the big one has a mass about 10 times that of the supermassive black hole at the center of the Milky Way. That means you would need to count about 31 billion collisions, and at one point in this virtual process, the frequency of clacks would be around 100 billion clacks per second. So let's just say that you would need very good numerical precision to get this working. I'll emphasize again that this process is way over ideal.
Funny.
But in real physics. But of course, you all know this is not interesting because of its potential as an actual pi computing algorithm, or as a pragmatic physics demonstration. It's mind-boggling because why on earth would pi show up here? And it's in such a weird way.
Take photos!
Its decimal digits are counting something, but usually pi shows up when its precise value is describing something continuous. I will show you why this is true. Where there is pi, there is a hidden circle, and in this case, that hidden circle comes from the conservation. You're going to see two separate methods, which are each as stunning and surprising as the fact itself. Delaying gratification, though, I will make you wait until the next video to see what's going on. In the meantime, I highly encourage you to take a stab at it yourself, and
What do you think, pies? I don't know.
The
What
task.
happened?
Simply choose a design template you like. Add the
With Happy Pie, you can make a app as easy as pie. Is that why I'm all the way to Pi? And I can't even make an app, I have to pay.
last video, I left you with a puzzle. The setup involves two sliding blocks in a perfectly idealized world where there's no friction and all collisions are perfectly elastic, meaning no energy is lost. One block is sent towards another smaller one, which starts off stationary, and there's a wall behind it, so that the smaller block bounces back and forth until it redirects the big block's momentum enough to fully turn around, sailing away from the wall. If that first block has a mass which is a power of 100 times the mass of the second, for example, 1,000,000 times as much, an insanely surprising fact popped out. The total number of collisions, including those between the second mass and the wall, has the same starting digits as pi. In this example, that's 3,141 collisions. If that first block was a trillion times the mass, it would be 3,141,592 collisions before this happens. Almost all of which happen in one huge, unrealistic burst. And speaking of unexpectedly big bursts, in the short time since that video went out, lots of people have been sharing solutions and attempts and simulations, which is awesome. So why does this happen? Why should pi show up in such an unexpected place and in such an unexpected manner? Foremost, this is a lesson about using phase space, also commonly called configuration space, to solve problems. So rest assured that you're not just learning about some esoteric algorithm for pi. This tactic here is core to many other fields, and it's a useful tool to keep in your belt. To start, when one block hits another, how do you figure out the velocity of each one after the collision? The key is to use the conservation of energy together with the conservation of momentum. Let's get into the process. At any given point, the total kinetic energy is 1/2 m1 times v1 squared. The total momentum of the two blocks is m1 times v1 plus m2 times v2. This also has to remain constant when the blocks hit each other, but it can change as the second block bounces off the wall. In reality, the second block would transfer its momentum to the wall during this collision, and again, we're being idealistic, say thinking of that wall as having infinite mass. So such a momentum transfer won't actually move the wall. So here we have two equations and two unknowns. To put these to use, try drawing a picture to represent the equations. You might start by focusing on the energy equation. Since v1 and v2 are changing, maybe you think to represent the equation on a coordinate plane, where x is equal to v1 and y is equal to v2. So individual points on this plane encode the pair of velocities of our block. In that case, the energy equation represents an ellipse, where each is root of 10. Likewise, have the y-axis. Conservation of energy tells us that we must jump to some other point of the circle, but which one? Well, use the conservation of momentum. This tells us that before and after the collision, the value of m1 times v1 plus m2 times v2 must stay constant. In our rescaled coordinates, that looks like saying squaring the total number of collisions turns into counting the total number of hops along these lines, alternating between vertical and diagonal. But our question remains, why is it that when that mass ratio is a power of 100, the total number of steps shows the digits of pi? Well, if you stare at this picture, maybe, just maybe, you'd notice that all of the arc lengths between the points on this circle seem to be about the same. It's not immediately obvious that this should be true, but if it is, it means that computing the value of one such arc length should be enough to figure out how many total collisions it takes to get us into that end zone. The key here is to use the ever-helpful inscribed angle theorem, which says that whenever you're forming an angle using 3 points on a circle, P1, P2, and P3, like this, it will be exactly half of the angle. This arc length between those two bottom points, measured in radians, will be 2 theta. And importantly, since the momentum line has the same slope for all of those jumps from the top of the circle to the bottom, the same reasoning means that all of these arc lengths must also be 2 theta. For example, if theta was 0.01 radians, then multiplying it by as much as 314 would keep you below pi, but multiplying by 315 would bring you over that value. So the answer would be 314. Meaning, if our mass ratio was one such that the angle theta...
3.1... 1 second. 3.14159 3.14159 3.14159
blocks would collide 314 times. So now, you know what we need to do. Let's go ahead and actually compute the value theta. Say when the mass ratio is 100.
Bruh, 0 is nothing. It's the smallest number, but it's literally nothing. It's invisible.
Momentum line was the negative square root of m1 over m2, which
That's not
is
zero.
-10.
That's not
That would
zeta.
mean that the
That's
tangent
not
of this
alpha.
angle theta
That's
opposite
not
over
pi.
adjacent
That's not
run
tau.
over the negative
That's not
rise,
alpha.
so to speak,
That's not
which is
rho.
1 divided by
That's
10
not
in this
alpha.
example. So theta is going to be the arctan of 1/10. Speaking more generally, it'll be the inverse tangent of the square root of the
That's
small
not
mass
eta.
over the square. If you go ahead and plug these
Here's
into a calculator,
eta, but I
what
think
you'd notice
it's
is that
not
the
get
inverse
here.
tangent of such a small value is actually quite close to the value itself. For example, arctan of 1 over 100, corresponding to a big mass of 10,000 kilograms, is extremely close to 0.01. In fact, it's so close that for the sake of our central question, it might as well be 0.01. And what I mean by that is, analogous to what we saw a moment ago, adding this to itself as many as 314 times won't surpass pi, but the 315th time would. And remember, unraveling why we're doing all this, that's a way of counting how many jumps on the phase diagram gets us into the end zone, which in turn is a way of counting how many times the blocks collide until they're sailing off never to touch again. So that, my friends, is why a mass ratio of 10,000 gives 314 collisions. Likewise, a mass ratio of 1,000,000 to 1 will give an angle, theta equals the inverse tangent of 0,1. And again, if we ask...
I feel like he only posts his pi video because look at his channel banner.